Hello everyone. So today we're doing yet another complex number. Namely, we're supposed to find the real part of z and the imaginary part of z if z is equal to the natural log of 1 plus I quantity to the power of I. Okay, to actually do this problem, the first thing that we should do is look at the number in the numerous. So let's call it instead of z1, z asterisk. So let's call z asterisk 1 plus I. And let's go ahead and look at it in the complex plane. Okay, so this is our imaginary axis, and this is our real axis. Okay, so if this is 1 and this is 1, here is approximately our number. Okay, so it lies in the first quadrant. Of course, this is the algebraic form of our complex number, z asterisk, and what we want to do is convert it into its trigonometric form. Or, how do we go about doing that? So, the algebraic form of a complex number is x plus iy, and its trigonometric form is equal to r times cosine of theta plus I times sine of theta. Okay, so this here is y, this here is x. This distance right here is r, and this angle right here is theta. So from the picture, it's obvious that r must be equal to the square root of x squared plus y squared by using the Pythagorean theorem, which is exactly the same as square root of 1 squared plus 1 squared, and therefore r is equal to the square root of 2. Great. And also when you look at the picture, it's obvious that theta must be equal to the inverse tangent or arctangent of y over x, which is the same as arctangent of 1 over 1, which is just the arctangent of 1. And the arctangent of 1 has multiple values, but since this complex number of ours lies in the first quadrant, we will take a value of theta from the first quadrant, which is pi over 4. So that means that our z asterisk is equal to the square root of 2 times cosine of pi over 4 plus I times the sine of pi over 4. And let's go ahead and remember Euler's identity. R times e to the power of I theta is equal to r times cosine theta plus I times sine theta. Or in other words, z asterisk then must be equal to the square root of 2 times e to the power of I pi over 4. Okay? Now let's just go ahead and rewrite the square root of 2 as e to the ln of square root of 2, assuming its principal root, and multiply that by e to the power of I pi over 4. So that means that our z asterisk must be equal to e to the power of ln of square root of 2 plus I pi over 4. Great. Now let's remember what our z asterisk is. That's our quantity from right here, 1 plus I. Okay? So let's go ahead and plug that back into the original equation. So z is equal to the ln of z asterisk, which is exactly the same as e to the power of ln of square root of 2 plus I pi over 4, and this quantity goes to the power of I. Now once we multiply the exponents, we'll get the ln of e to the power of I times ln of the square root of 2 plus I squared, which is just negative 1 times pi over 4, so it's going to be minus pi over 4. And now finally we can use the property of the natural log to pull out the exponent in front of the logarithm, and ln, and we'll be just left with, so I times ln the square root of 2 minus pi over 4 times ln of e, and ln of e just cancel out there. Ln of e is equal to 1. So z, and I'll write it in this order, is equal to negative pi over 4 plus I times the ln of square root of 2. Now this here is the real value of z, and this here is the imaginary value of z. I'll write that down nicely. So real part of z is equal to negative pi over 4, and the imaginary part of z is equal to the natural log of the square root of 2. So that's our final answer to this problem. I hope you enjoyed the video. If so, leave a thumbs up and subscribe. I'll see you in the next one.